Awesome. Okay, cool. Yeah, so today I'm going to be talking about optimizing and abstracting prompts with DSPy. So the whole goal of this is to say goodbye to prompt engineering, essentially. And DSPy, which I'll get into in a little bit, is a framework out of Stanford NLP. And as was mentioned before, I'm a grad student at Cornell Tech. So what's the problem with prompt engineering? There's really two main problems. I know there's three things kind of separated here on the slide, but the two main problems are that it's quite labor intensive, can lead to a lot of trial and error. And then it's also hard to scale when it's labor intensive. So it's kind of impractical to generate prompts manually for very large systems. And there needs to be a way to kind of optimize this and streamline this process so that it's very simple, intuitive, and quick, so it doesn't take so long. And then another key thing here is that prompt design demands a deep understanding of both AI models' behavior, the data within the AI model, and the inputs and outputs, as well as domain-specific knowledge. So requiring specialized knowledge is very important in order to generate prompts that are effective in giving good outputs. So what is DSPy? DSPy is a framework for programming language models, and it's designed to program language models through modular components. And this is aimed at moving on the traditional prompt engineering. So essentially, the goal is to kind of abstract away prompt engineering as much as possible. And DSPy is used for optimizing and fine-tuning prompts of modern LM systems or language model systems. So there are a few key use cases that the DSPy library and framework provides solutions for. And we're going to get into one of these in more of a deep dive, but generally, we can see things like chain of thought reasoning, retrieval augmented generation, multi-hop QA, document summarization, React agents with disposable tools, entity extraction and classification as all things that can be tackled with the DSPy framework. So it's a very powerful framework, and there's a lot of things you can do with it. So as I said before, the whole goal of DSPy is to say goodbye to prompt engineering. And there's a very cool article I recommend to read by Lawrence Liu on PH Data. And he's basically discussing and explaining this. And it abstracts prompt tuning away from humans. And at a high level, this is done by algorithmically optimizing a prompt towards maximizing a given metric by comparing prompt output results to an evaluation data set. So to sum it up in this diagram here, what we can see is that all the developer has to do now to generate these really effective prompts are define the expected behavior. And this is generally done by providing input and output examples. And this is done with a signature, what is called a signature in DSPy. And we'll get more into that in a little bit. And then you also create or use an existing evaluation metric to evaluate against so that we can optimize the DSPy program. So after that is done, all you really have to do is use the DSPy optimizer and start the optimization. It iteratively fine-tunes a prompt to maximize the evaluation metric of the provided examples. So another cool thing about DSPy is that it's inspired by PyTorch's modular design. So essentially, there are complex functionalities within both of these frameworks, and the way PyTorch works is through modules. So we have this class here as an example is a neural network. It inherits from a neural network module, so it has a bunch of different properties within that, and then it builds on top of it. So we also see similarities in terms of these class-based structures or modules that are built for programmability and also for generating models, or in DSPy's case, programs or agents. So this is really good for clarity and reusability. It's quite intuitive. And then they both also use the initialization method and the forward method, which is, that's kind of one of the main mirrors of PyTorch within DSPy. Obviously, they're very different frameworks that tackle different problems, PyTorch being for building models and then training models. DSPy is kind of more high level, and it's for training these programs or agents or language model applications. So this gets into a big part of this presentation, which is MePro v2. And this is multi-prompt instruction proposal optimizer version 2. And there's a really good paper on this. I recommend reading it. This link is here. But essentially what happens is this is an optimizer that enhances performance by both optimizing the instructions and the few shot examples. So in the past, DSPy has offered CoPro, which is another optimizer. And by basically what CoPro would do is only optimize the instructions, but it would fail to really optimize few shot examples, which can be generated or augmented or pulled directly from the training data. So what's really cool about MiPro v2 is that it optimizes both the instructions, which you could think of as like system instructions for a prompt, as well as optimizing the few shot examples, which it can generate through bootstrapping or pull directly from the training set. So how does it work? Essentially, it aims at maximizing a downstream performance metric, such as an accuracy or F1 score. So usually this is going to be some sort of accuracy metric. And without access to, it does it without access to the module level labels or gradients. So it's kind of very abstract. And essentially, we are just trying to get better output values for our entire program, right? And we're optimizing for that. So the way it works is it bootstraps few shot examples. So it generates candidate examples by sampling from the training set and validation outputs. And these can be question answer examples, for instance. And then it also proposes instruction candidates. So it creates instructions based on the task dynamics, program code, data summaries, and few shot examples. And then lastly, it has this key feature here with Bayesian optimization, which essentially allows for search to find an optimal combination of instructions and examples. And this is how it selects the optimal few shot examples that are used in the final model to get the highest accuracy. So essentially what we're doing here is finding the best combination of prompts, and we're generating stuff along the way to get the highest accuracy at the end for our language model program. So to briefly go over the setup of the code for this, you need to install the DSPy library, and definitely recommend using Python, very intuitive. Configure the language model in your environment. So this would just be importing. And then we'll get into this in a second, but there's many different language model providers that you can use. I used OpenAI for this example. Then we configure the program. So this is what I was going back on before with the modular approach to programming these types of applications or types of programs. So here, this is a chain of thought example, which I'm going to dive deeper into in a bit. But essentially, we set this up here, and we have this signature. So this is defining kind of the flow of data, and we're going to input a question and what we want to output an answer. And then we also have this forward function for defining execution. And then finally, we can run this program, and it makes use of the OpenAI model that we're using, and then we can print the response. So to quickly go over compatible providers, this is the current version. We can use OpenAI, Anthropic, Databricks, local LLMs on GPU servers, local LLMs on your laptop, any scale models, Together AI, Amazon SageMaker, and Microsoft Azure. I know there's not compatibility currently for Gemini, but hoping that comes by soon because I'm a big fan of Gemini and want to build more with this. So with that being said, I'll go into a little deep dive of a code example for how this works and how we can optimize a chain of thought program. So this is a QR code that you can use to go to this notebook, but I'm just going to click on this to go to it directly. I'm just going to open it here then. So let me see if this works. Yeah. Basically, in the code here, what you can see is we install the required packages, skip over that. We import and configure the language model for DSPy. So this is what I do here I use GPT-4o Mini, and I use the OpenAI key, which I have. I believe it's in user data. Yeah. So I use Colab user data for that. And I'm using the grade school math 8,000 data set. And this is essentially just grade school math problems. And this is basically a good data set to use for running chain of thought problems. So essentially getting a question answer or having a question answer type of, I guess, like structure, but also within it, you will want to have like a reasoning as to why you come up with an answer. So whenever you're going about a grade school math problem, we want the LLM to reason as to why an answer is a given way before it actually spits out the answer. So this is the module that I discussed earlier. Sorry. This is the module that I discussed earlier. And here we evaluate it with zero-shot setup. So this is essentially just prompting directly with no prompt that we've optimized, right? So
hey, Jasper, we can't see your thing you're sharing right now.
Oh, okay. Let me try to reshare. Sorry about that. Can you see it now?
Yeah, perfect. Yeah.
Cool. All right. I'll just briefly go over what I might have missed. We have installation up here. Then we import and configure the language model. So we instantiate it with GPT-4o Mini and use the OpenAI key for that. Using the grade school math problem dataset as mentioned above, or as mentioned before. And then we define the chain of thought module, which is what I went over in the previous slides. So this is essentially what we're optimizing the prompt for. And as we can see, again, very similar to PyTorch's kind of modular layout for training. And then the next step is evaluating with a zero-shot setup to essentially see, without any examples or without any tuned prompt, how high is the accuracy that we're currently getting. And we see that we have an 86.3% accuracy, so it's not bad. So now I'm going to get into a bit of optimization. And here we set up the optimizer. So the optimizer has a few different modes. We have light mode, which is a less extensive search, and it's cheaper. And then we also use medium mode in this example too, which I'll get into later. But what we're doing here is we're essentially running the optimizing. We're optimizing this program that we came up with here, right? And we're also keeping track of the history so that we can calculate total tokens and total cost. So we have visibility over how expensive this tuning is going to be in terms of cost and tokens. So yeah, as you can see, this is just the verbose output for the tuning and optimization. And for this example, we have this many tokens used, and it costs 9 cents, which isn't bad. And then, as we see here, when we evaluate this trained or with the tuned prompts, we actually get a higher accuracy. As opposed to 86, we get 92, which is great. So clearly this works, and we want to kind of look into trying different hyperparameters for this. So this is just an example showing what I just mentioned. And here, this is also pretty cool. We get to see the few shot examples with the reasoning. So these are the ones that are included in the prompt actually before we run the new evaluation. So these are the ones selected by our optimizer. So yeah, now we can look at, sorry, 1 second. Yeah, so this is another example of just using a different setup with hyperparameters, which I'll get into in a bit. We can just skip over this. We see it has a lower accuracy, but still higher than the zero-shot accuracy. And then here is another example. Also, this includes the system instructions this time. So essentially, this is the optimized system instructions on top of the few shot examples generated for this tuning. Finally, we have another one with separate hyperparameters as well, a different setup. And then we get a higher accuracy of 93%, which is great. And then we also can see the cost is similar with the light mode, and also the tokens used is similar. Yeah, so then I'll go into medium mode, which is essentially a more extensive search, and this takes longer to run. Skip through this for a bit, it's verbose output. And then what we can see is that we actually have the highest score we've seen so far, which is really cool. So yeah, essentially, also, here, let me go down to this. Okay, so very interestingly, we see that this costs about 50 cents, which is a lot more, about 5 times the cost of the light mode. And it has kind of marginal returns. It's a little better than the 93% or the 93 accuracy that we had before, but it's not really significant given the amount of cost or the magnitude of cost more it costs to run this. So yeah, and we can see, I'll just skip through the last examples because it's essentially the same thing with different hyperparameters, training on the medium mode. And yeah, I compiled the data, and I'll just go back to the slide real quick to go over the data that we collected from this. So for our optimization results, we have here we see the zero shot has the lowest accuracy, and this is zoomed in, keep in mind. So we also see that there are like significant improvements using the light mode. Oops, sorry. Yeah, so there are significant improvements using the light mode for these 3 light mode hyperparameter settings, and that's great. And we also see for medium, we have actually the best with the original hyperparameter settings that we set up. We have the best accuracy, and that's great. But it's really interesting that as we spend more with tuning, we don't really see a necessarily equivalent, I guess, improvement in accuracy, right? So there is very much a diminishing return happening here. So here we kind of see again that there is essentially a diminishing return here in terms of accuracy. So here we're including more augmenting examples, which essentially means we're including more generated bootstrapped examples. And we're still getting like pretty similar accuracy as this one over here. And then these ones are more interesting. Here we see as we increase the cost that we are the spend for tuning these programs, we still improve our accuracy, but it's kind of marginal after this point here. So this begs the question of like whether or not we actually need to spend this much money, or if we can get away with just using the light mode and kind of optimizing with these hyperparameters. And then we also see something similar here with unaugmented examples, but yeah. So briefly to go over other use cases, there's RAG, as I mentioned before, and we can use semantic MiPro v2 with a semantic F1, essentially to optimize prompts for RAG systems. So very similar process, just with a RAG use case. And then with React agents, this one's really cool. We can optimize for a React agent, and this involves optimizing multiple prompts and few shot examples, potentially for different tools, with the goal of collectively maximizing a metric for the entire agent system. So everything is kind of abstracted when you create a React agent, and this is all done under the hood, so you don't have to worry about the individual modules and tools that you're using. And then finally, we also have multi-hop QA. So this is a really big use case for this type of prompt optimization, and we can use MiPro v2 with a top recall metric or top 5 recall metric or so on. And this can also improve the recall of the multi-hop answer documents. So essentially, are we getting the golden documents that are necessary to answer the question, the current question given to the model? So yeah, and this is just a small example of the code for a React agent using DSPy. Yeah. So,
awesome. Yeah, thanks so much, Jasper. This is like an amazing talk, I guess. Anything else? Yeah.
Yeah. Just this is the final slide. Sorry if I'm going a little over, but just mentioning the difference between key frameworks. So like, why would I want to use this over LangChain, Llama Index? So these frameworks are really cool, and they help developers build agents and retrieval pipelines. But the key here is that these still often require developers to rely on manual prompt engineering, and DSPy is really good at automatically prompt engineering or automated prompt engineering, and basically eliminates all this manual prompt engineering that's necessary. And as we can see with the coding example, we had an increase in accuracy with that, so it was great. It also provides a modular structure, and it's very intuitive. I know there's a very big learning curve for some people using LangChain at first. And it's also built around this automatic optimization fine-tuning. So it's really the goal of using DSPy is more for observability and also optimization of the entire pipeline or the entire program that you're building. Yeah, and that's it.